Hi, this is Jamin, and today I want to talk about a question that comes up a lot in space travel, and that is, how do you cross the light barrier? Recently, Sabine did a video asking whether faster than light travel is fundamentally possible. I'll list the video link below so you can watch it yourself. And she's absolutely right about asking the standard question. According to special relativity, as you approach the speed of light, the energy required goes to infinity, so nothing with mass ever gets there. But I want to look at the same question from a slightly different angle. Because Einstein actually gave us not just a speed limit, he gave us a relationship, and that is energy, momentum, space, time, and motion are all tied together by very specific equations. And those equations tell us exactly where the problem appears. In the simplest form, relativistic energy looks like this, where E equals m naught, the invariant mass, times c, the square speed of light, times the square root of the Lorentz factor. And I'm sure everybody has seen this. And we can see that as velocity approaches the speed of light, the denominator goes to zero and the equation blows up. That is where the infinity comes from, not from space itself, not from time, but from the way the energy scales with velocity. And here's the part we almost never question. We quietly assume that the numerator stays fixed, that the way energy couples to motion never changes, no matter how extreme the situation becomes. But physics does not usually work that way. In quantum field theory, in gravity, and even in Einstein's own field equations, coupling terms evolve with scale. So instead of asking whether relativity forbids faster than light motion, a better question is this. What if the energy coupling itself depends on the velocity? One way to write this is by using a modification to the equation. And in this, we have energy is equal again to the invariant mass times the speed of light squared, and again the Lorentz factor, but I've added in this function f of v. This does not change relativity, it just makes explicitly something we usually leave implicit. The function f of v controls how energy responds as you approach light speed. If it stays constant, nothing new happens. You recover the standard divergence equations, but it does not have to stay constant. Now, one example of such a function is the one listed on the screen where f of v is equal to the hypertangent function with velocity terms inside, and the denominator just scales this function when v, the velocity, is equal to 0. You do not need to know all the math details here. All that matters is that this function is smooth, bounded, and changes rapidly near the speed of light, allowing us to cross the light barrier. Now, this function gives us three possible behaviors. If f of v changes slowly, the energy still diverges. If it softens moderately, the divergence is delayed. But if the gradient steepens near the speed of light, the numerator collapses fast enough to counter this relativistic blowup. In that case, the total energy remains finite, the light barrier does not vanish, but it becomes crossable without violating any of Einstein's equations. So we see here nothing locally exceeds the speed of light, causality is preserved, space-time still behaves exactly the way general relativity demands it. What changes is how energy is distributed in the extreme regimes. So crossing the light barrier is not about cheating relativity, it's about understanding it more deeply. The real question is not whether this is forbidden, it is what physical mechanism can generate a function like f of v, a step function. And that is no longer a philosophical question, it is an engineering one. If you've enjoyed this video, I would appreciate a like and a comment in the section below, and we'll see you next time.